Can you see the PowerPoint?
Yes, sir.
Right. So today I'm going to uh, talk about hypothesis testing. And there is a complete chapter in the book. I think it's chapter 4 or 5, which talks about hypothesis testing, but I'm not going to go uh, into that much detail. Of course, the gist will be here, so it will be a great idea if you read the whole chapter, or you can follow this uh, presentation of mine to understand hypothesis testing. Of course, I'll be talking about hypothesis testing in multiple regression also, so there will be a repetition of the same thing. Uh, but the basic idea remains the same. And for conceptual understanding and application and numericals, I'm keeping everything in mind, and I'll be talking in those terms here. So, to have a recap, what we started with PRF and SRF, and I said that we have a population regression function like this, and we we don't have complete population data on Y and X. So we take a sample and then we fit the same. We use OLS and we fit a line to the sample data, and that line has this address: beta 1 hat plus beta 2 hat xi plus ui hat, and these ui hat are the residuals. Beta 1 hat is an estimator of beta 1, beta 2 hat is an estimator of beta 2. Then we had a discussion on how to calculate beta 1 hat and beta 2 hat. Beta 1 hat and beta 2 hat were calculated using OLS. Right. Now that we have calculated beta 1 hat and beta 2 hat, we also calculated their standard errors. Now, then I said that standard errors are the connect between beta 1 hat and beta 2 hat, sorry, beta 1 hat and beta 1. Similarly, beta 2 hat and the true population parameter beta 2. So because our goal is to have an idea about beta 1 and beta 2, and what we have are the beta 1 hat and beta 2 hat and their standard errors, now we are in a position to say something about beta 1 and beta 2 using beta 1 hat and beta 2 hat. And this is done using hypothesis testing. So we will be testing hypothesis, and there are two conflicting hypotheses. One is called the null hypothesis, and another is called the alternate hypothesis. The null hypothesis in regression, when we are testing about population parameters beta 1 and beta 2, is going to be that beta 2 is equal to 0. And the alternative hypothesis is going to be everything which is not there in the null. We call it H1, and it means beta 2 is not equal to 0. Now the question is that why do we have such a hypothesis? Why do we test such a hypothesis? The reason for testing this hypothesis, whether it is true or not, testing means we want to check whether null hypothesis is true or the alternate is true. One of them is going to be true, right? Which one is true? So if we have only two options. One option is to reject the null, reject the null, or not reject the null. We have only two options. So our result would be in terms of these two options. Whether we are going to reject the null or we are not going to reject the null, right? And it all depends on these things that we calculated. And now I was talking about why do we have such a hypothesis? What does beta 2 equals to 0 mean? What is the meaning of beta 2 equals to 0? Anyone? I'm asking a question. If beta 2 equals to 0, what does it mean?
And that means that the regression function has no slope and it's a straight line.
Right,
It is just an intercept.
right. Very good. So if we are saying that the null is true, if we could not reject the null, it means beta 2 is equal to 0, which means slope of the PRF is 0, which means our PRF is like this. This is our PRF, right? So we have an intercept called beta 1, but the slope is 0. So it is flat, right? Now, if the slope is 0 and the PRF is flat, it means there is no relationship between x and y. You can think of the PRF, you can see the PRF and understand this part. PRF says and you can see if beta 2 is 0, then your PRF is beta 1 plus ui, where beta 1 is a constant and ui is the random error term. There is no x here. Beta 1 is there, but there is no x. So when there is no x, it means y does not depend on x. So we conclude that there is no relationship between x and y. We conclude that x does not affect y. We can say in other words, y does not depend on x. Or in other words, there is no relationship between x and y. So we got this sort of conclusion if we could not reject the null. Now think about, why are you doing regression? You took one y, you took one x, and then you ran a regression, and then you found that you could not reject the null, and then you found that there is no relationship between x and y. So you started this whole process of analysis, which is called regression, to check whether there is any relationship between x and y, and then you found there is none. So you must be thinking that there is some relationship, therefore you started doing the regression. Had there been, if you would have known that there is no relationship between x and y, you would not have started doing this analysis and this whole regression, if you were sure about this. But because you were thinking, yes, there is a relationship, and you wanted to know what is the relationship, how much is the relationship, what is the quantitative aspect of the relationship. So you started doing this regression, and then you found that you could not reject the null, and then beta 2 is 0. That means the PRF is flat. That means x does not affect y. That means there is no relationship between x and y. So you would not be happy as a researcher. So researchers want to reject this null. They would like to reject the null. And they are looking for evidence in this whole analysis that we are learning to say, just at the end of that, they just want to reject the null, right? Because if the null is rejected, the the result is, if you are able to reject the null, that means your null is not true. That means your alternative is true. That means beta 2 is not 0, but it is something else. It may be a positive number, it may be a negative number. So in this regression, when beta 2 is not equal to 0, that means it will stay here. And suppose you found that, I mean, we can't find it like this, but I'm just for explanation purposes, I'm assuming suppose beta 2 is equal to 2. I mean, we will never get something like this, that beta 2 is 2. But for explanation purposes, I'm using this. Suppose you found that beta 2 is equal to 2, it means if x rises by 1 unit, y also rise, but by 2 units, right? So this is one situation. Suppose beta 2 is equal to -2. It means if x rises by 1 unit, y falls by 2 units. Right? So that sort of conclusion you can get. Of course, we can't get beta 2 equals to 2 or beta 2 is equal to -2. But if you got it, you would say something like this. And this is, we are talking about PRF. So we are talking about population, right? That's the reason why we will never know this. But suppose if you know this. Anyways, so beta 2 is not equal to 0 means it can be positive or negative. If it is positive, you would make a statement like this. That means there is relationship, and you can quantify the relationship by the second expression sentence, that if x rises by 1 unit, y also rise by 2 units, or if x rises by 1 unit, y falls by 2 units. So you have quantified that by how much change in x, how much y changes, and you will be happy with the result in the sense that you are able to verify that there is a relationship between x and y, and you are able to quantify it, right? So that's what happens when you have these two conflicting hypotheses, the null and alternative, and you have to find which one is true, and then you found which one is true, and then if you find the alternative to be true, you are happy. If you found the null to be true, you are not happy. So I just gave a background of this hypothesis testing. Now let us come. If you have any question here, you can ask. Any question?
No, sir, understood.
All right. All right. So let's come into the actual mechanics of hypothesis testing. So what we do is, as I said, as we discussed about sampling distribution, right? And mm, sampling distribution is nothing but if you have a population size of 100 and you are taking a sample of size 10, then if you want the sampling distribution of a parameter, if you're running a regression and you want to have a sampling distribution of beta 2, suppose, then you have to collect all possible samples of size 10 from the same population of size 100. And for each sample, you have to calculate beta 2, and then you have to record it. I mean, this is going to be beta 2 hat, right? Because you would be running a regression on sample of 10 each time, right? I'm talking about all possible samples. So for all possible samples, you are running a regression like this: yi equals beta 1 hat plus beta 2 hat xi plus ui hat. So you are running this regression for each sample of size 10, and every time you are getting a beta 1 and a beta 2 hat, and then there are a lot of samples possible. So for each of the sample, you record your beta 2 hat here, and this is known as sampling distribution of beta 2, right? It's a sampling distribution of beta 2, which is a population parameter, right? Because you are sampling from the population and you have got all possible samples, right? And when all possible samples are there, means every possibility is there. Of course, what you're recording is beta 2 hat, but this sampling distribution is of the population parameter beta 2, right? So there is some completeness in sampling distribution. For example, well, when you talk about population, population has completeness, right? It has everything. And sampling distribution also has completeness in the sense that it is the distribution of a population parameter using the samples, all possible samples. This statement is important, all possible samples. So because there are all possible samples which are being collected, there is a completeness in sampling distribution of any parameter. So we are talking about the parameter beta 2, which is the slope of the PRF. This is the sampling distribution of beta 2. And what we are recording is beta 2 hat for each and every sample which is possible in that population, right? But the thing is that this sampling distribution has completeness. It has one more parameter, that is sample size, right? So you can have other sampling distributions for a sample size of 11, other sampling distribution of the same parameter. If you take a sample size of 20, you will have another sampling distribution. Of course, that would also be the sampling distribution of beta 2, and you would be recording beta 2 hat again, but that would be with respect to all possible samples of size 20. So that's one more parameter, but we can definitely say that there is a sort of completeness when we talk about sampling distribution of a parameter, right? So that is what is sampling distribution. Now, what distribution does it follow? The question is, what is the distribution or let me put it like this. What is the shape of this sampling distribution? We are interested in the shape, right? We are interested in the mean. We are interested in the variance, right? So we want to see it. Now, again, I'm not going to prove it, but the distribution which is meant, which we will be concerned here with regards to beta 2 hat and the population parameter beta 2, and also for all the regression parameters, beta 1, beta 2, beta 3, beta 4, whatever we have, it's a T distribution, right? It's a T distribution. right? So it means that we already know, and uh, we are not going to prove it in this course, and but you have to take this point for granted, that it is the t distribution which is followed by beta 2 hat and beta 1 hat when we are talking about beta 2 and beta 1, and also other betas which we will be doing in future in multiple regression, right? So that follows t distribution, and the t distribution is similar to normal distribution. In fact, very similar. It's like a normal distribution, right? A normal distribution has two parameters. One is mean, another is variance. And a t distribution also has two parameters, mean and variance. So you can completely define a t distribution by knowing the mean and variance. We will be using t distribution to test our hypothesis in case of population parameters beta 1 and beta 2, and also if in multiple regression beta 3, beta 4, beta 5, right? So how would we actually be testing the hypothesis? Let's talk about that. So what we do is we have a distribution, and we have beta 2 hat and beta 2 both on the x-axis, right? And there is a mean of the sampling distribution of beta 2, and that mean is expectation of beta 2 hat, and there is a proof which we will see, it is equal to beta 2, which is the true population parameter, right? And it is in the center here, because t distribution is like normal distribution, it is symmetric. So the left and right sides are mirror images of each other, and the mean is in the center, uh, and the shape is bell shaped. So it is very similar to normal distribution. So there's a mean here. Now we calculate beta 2 hat to be, suppose, in our example, how much did we calculate? Do you remember beta 2 hat, the example that we were doing? Okay, let me check that. I'll use those numbers, so that will be
Minus 0.5.
minus 0.5. Great. And also tell me the standard error.
So it was 1.290944.
Is it right, what I've written?
So standard error of beta 2, sorry sir, it's 0.64. 0.6454972.
Is it right?
So I cannot see it. It's
It'll
coming.
it'll be there.
Yes, sir.
All right. So we have a distribution here. I'm sorry, I'm not able to draw the graphs well here. So this is a T scale, or let me not write a scale, that would confuse you. Let me write T values. Let me write a T only, that's good. So what we do is, coming from beta 2 on the x-axis, we convert it to a T scale, and we convert each value in above graph to each value in the below graph, right? And the below graph is on a T scale, and the above graph, graph A is on, we have beta 2 hat and beta 2 value. So that's a scale, right? It's on that scale. Now beta 2 can be 1000 in one example, beta 2 can be 1.2 in another example, it can be 0.1 in another example. So that's some scale here, right? And it's going to vary according to x and y values. So in some cases, when you're talking about GDP and you're talking about thousands and thousands of dollars, or you are talking about billions of dollars, then your beta 2 would be of that measure in billions, right? So we have different scale according to x and y values as regards to beta 2 hat and beta 2, right? What we do is we convert it to t values, right? The shape of the distribution is same, there is one to one correspondence, and we if this is the first thing that we do, right? And that t value is equal to the value of the parameter, the sample statistic divided by the standard error of the sampling of the sample statistic. So what we have to find is minus 0.5 divided by 0.6455, right? So you can use your calculator to calculate this, and please tell me what it comes.
So minus 0.774.
Great. So we got we got our t statistic here, right? And that means our t statistic is here. Right? So t has a mean of 0, and it is same as it is the counterpart of of expectation of beta 2 hat here, and we have a t statistic which corresponds to beta 2 hat of minus 0.5. If I extend this, this is minus 0.5. So now we got a corresponding t value, which is negative, where our beta 2 hat was also negative, and the denominator can never be negative. Here in the t statistic, standard error can never be negative. So whatever sign is there for beta 2 hat, it's the same sign will be taken by the t value, right? Now, there are two types of tests. We can have a two-tailed test or a one-tailed test. Uh, In this case, it depends on our null and alternative hypothesis. If you have a system like we have here, that our null hypothesis is beta 2 equals to 0, and the alternative hypothesis is that beta 2 is not equal to 0, it tells us that it's a two-tailed test. right? We have an example of one-tailed test. If we write it like this, beta 2 is greater than equal to 0, or let me put this sign, it's not the right way to write. Beta 2 is equal to 0, and alternative hypothesis is beta 2 is greater than equal to 0. If we have a situation like this, it's going to be a right tail test. Right? And if you change the sign of the alternative hypothesis to less than equal to, it's going to be a left tail test. Right? So here we are having a two tail test. So we always have a two tail test. We can do a right or a left tail test also if we want in regression. It's not that it's not permissible, but in that case we should know if we have a very strong evidence that that either beta 2 will be 0 or it will be greater than or greater than 0. Sorry, I have written again, I have written in the wrong way. Let me write it again. Beta 2 is equal to 0, beta 2 is greater than 0, not equal to, because equal to is there already. So it's a right tail test. So we can do a right tail test also here, or we can do, I mean, in this case, we cannot do a right tail test because we have our beta 2 on the left side, in the left tail. So this is also not possible. What is possible here is a left tail test. So in this regression, we can do a left tail test also if we want. So we can do a left tail test also. Right? So why, I mean, how to choose between the two? If we have a strong evidence and understanding of the situation that there are only two possibilities, that whether beta 2 will be 0 or beta 2 will be less than 0, and there is no possibility of beta 2 being greater than 0, then in that case we can go with a left tail test, right? But generally we do a two tail test, and that's what we are going to see here as an example. So we are going to do a two tail test. That means we have no idea whether beta 2 will be 0, or if beta 2 is not 0, then will it be less than 0 or greater than 0? We have no idea about that. So we are going to check both the tails, right? So for checking for both the tails, we should have another value here, which is corresponding to this value, and it is equal to 0.774, but this is positive 0.774, right? Now, what is our goal? Our goal, what we want, ideally, we want to reject the null, right? So if you want to reject the null, you want your t value to be big. We want to reject the null. I'm going to we want to reject the null, therefore we want the t value to be large, right? We want our t value to be large, and further to the left or to the right. In the tails, we want our t value to be more and more into the tails, right? Now, there is something with the area here, right? So let me talk about that before coming to the final conclusion. So what is that area part? Now there is some area in the right, in the left tail and the right tail. And if I shade that area, this area and this area, I've shaded in the green. Green area is called the p-value. Green area is called the p-value. And the rule is, if p-value is less than or equal to 0.5, 0.05, we reject the null. So green area is the p-value of the t statistic, which is 0.774. Of course, if you change it to 0.874 or if you change it to 0.974, we are going to go more into the tails, and then p-value is going to decrease because there will be less area in the tails. So area in the tails is the p-value, and it's going to decrease if we increase the t value from 0.7 to 0.8 to 0.9. So as we want our t to be large, as I said, why we want our t to be large? Because we want to decrease the p value, because the rule is that p value should be less than 5% to reject the null. And because we want to reject the null, we want our p value to be less than 5% of the total area under the curve. And if we want less area under the curve in the tails, we want our p-value to be low, and then we are going to reject the null, and then we will be happy to establish relationship between x and y. So that's the whole idea of having a low p-value, right? So now why this 5%? This is another question. Why 5%? Why 5%? Why p should be less than or equal to 0.05? Why 0.05? What is so good about 0.05? Right? So what does this mean? That's the question. What does this 5% mean? So basically, we are saying that p should be less than 0.05. Basically, p is the probability of okay, I have to explain you type 1 and type 2 error before this. All right, so let us not go. We will do it tomorrow. I mean, next time. So let's not, let me not initiate that right now. So, and there are 2 minutes left, so I don't want to initiate it. All right, so we have 2 minutes. If you have any question, you can ask.
So that YouTube link.
I've shared it on the Google Classroom.
Okay, sir. Thank you, sir.
Yeah, I've already shared it, and each day I'm going to put the video on the same day. At least I can say that on the same day I'll put it, right? So today's video will be there today itself. I mean, I can do it as early as possible. I'll try to do it as early as possible. If you have any question, you can ask. Otherwise, that's it for today, and we'll continue this. And from here, I'll save this slide and I'll start from where I left.